Good afternoon, everyone, and thank you for showing up. This is the first seminar of the season, and today we have Shantanu Soumya, who is a fifth-year Ph.D. student in the Department of Mechanical Engineering here at UNH, and he works with Nathan on HC interaction stuff. And today, and prior to this, he did his Master's of Science in Civil and Environmental Engineering from Georgia Tech. Today, he will be talking to us about some of his recent stuff that he's been working for a while, like measuring of horizontal velocity gradients and turbulent kinetic energy at an undulating HC interface. So, over to you, Shantanu.
Thank you. Thank you for being here. Let's talk about ocean surface dynamics and what happens if there is surface waves and wind present right at the surface. So just to point out, this work was advised by Professor Nathan Larsak, and we had two external collaborators who worked with us. They were Ivan Savlev, he works at US Naval Research Lab in Washington, and Professor Christopher Zappa, who works at Columbia University. So before we even begin, let's talk about why should anybody care about what's happening at the surface of the ocean. Very first point would be the ocean surface acts as an intermediary for the heat and momentum fluxes that are transferred either from the air side on into the ocean or from ocean into the air. Now, these turbulent fluxes are characterized by the velocity gradients on the surface, as any turbulence and turbulence-related processes would be. Now, turbulent fluxes also contribute significantly to the coastal weather environment, bigger weather patterns. I want to say hurricanes, but it does affect those weather patterns. Also, for any wave modelers that we have here, surface turbulence or surface conditions at the ocean surface serves as the boundary condition for the flow fields that is below the surface. Okay, so let's talk about what are the challenges that are associated with making such a measurement at the ocean surface. I also have this. The first one would be, how do you make an unobtrusive true surface measurement? Because they are logistically challenging to make. And here I want to highlight the word true surface because people have different interpretations based off on the field that they're working in, different interpretation of what a true surface is. And in a few minutes, we will talk about what our interpretation and what we call a true surface. Another challenge that is associated with these measurements would be spatial velocity gradient requires simultaneous measurement of spatial velocity field. So if we want to calculate del u del x, we want to know what velocity u is at a particular location and the location right in front of it, or at a delta x, okay, at delta x spacing. Now, these are the general challenges, but another challenge that we created all by ourselves is how do you calculate the velocity gradient for an unstructured grid? We'll show what we mean by this in the later slides. So, what are the physics that we are trying to chase, that we want to capture because of the measurements that we are making at the surface? The very first would be what is the statistics of turbulence that is involved on the surface measurements or the flow field related to the surface? How does the turbulent flux respond to presence of surface waves? How does these turbulent fluxes depend on wind speed at very different? Now, due to the surface, we also want to know or look generally at the surface dynamics that takes place due to the interaction of surface current and surface waves. So what do we need what kind of measurements do we need for this? To start with, we will need a simultaneous spatial velocity field at the air-water interface. This is the basic thing that we need, or basic measurement that we need to make such a measurement, to change the physics that we want to look at the surface. Again, highlighting the word interface here, but apart from the basic requirement, wouldn't it be nice to have the measurement be unobtrusive? Remote measurements. Wouldn't it be nice if the measurement that we have has high spatial and temporal resolution? And would it be awesome if we have a structured grid? Let's look at different. Now, those are, going back 1 second. So these are the requirements that we have. Let's look at what kind of work, what investigations has been done in the past for characterizing surface velocity field, visualizing these fields, and then measuring them. So let's start with surface visualization. We'll start with the work of Melville et al. In 1997, who used tiny glass spheres, which were on the surface, which were imaged by a visible camera. So you see, the picture shows start of a flow of the flow wind from panel A to 5 meters per second. So panel A shows the flow field at rest. Panel H shows the flow field at 5 meters per second velocity. Now you'd see these structures that are being formed, and these structures were later recognized as what an infrared imagery would show. So another form of surface visualization is just looking at the ocean surface, ocean surfaces or interface surfaces skin temperature using an infrared camera. The surface has their own thermal signatures, and so you could visualize them. So in this plot, Savlev et al. This plot was shown in Savlev et al. 2020. And in this is remarkable because we have different visualizations for increasing wind speed. So lowest wind speed to the highest wind speed, and then also another characterization with wave steepness. So with how the wave steepness affects these passive tracers or surfaces thermal features. Now, okay, one quick thing to point out is that these features almost act as traces for the velocity profile at the surface. Now, if you look at this plot right here, you'd see over there, right here is a breaking wave crest or a breaking wave just propagating, right? So we could identify these microbreakers or even use these patterns or thermal features to track and find velocity. So leading into what passive infrared imaging would give. So those infrared thermal features that you saw in the previous image, if you track those within certain small windows, you could get your velocity measurement. You will get your velocity measurements within those windows. Usually people do cross-correlation technique, use cross-correlation technique within those small windows. Zishan is doing that kind of work right now. So, but this work was published by Sutherland in 2015, Sutherland et al. And these panel A, B, and C shows the velocity field with the velocity vector, and the dashed line shows the wave breaking region, the bore of the wave breaking region. Panel D, E, and F in these plots shows vorticity, surface vorticity that was calculated from the velocity field. They remarkably used this vorticity field and calculated vorticity spectrum, found and used that vorticity spectrum to calculate decay dissipation rate at the surface. Now, moving on, another work that was done by Laksag et al. 2020 was to use a vective surface technique where you stack up your thermal infrared images and then take a Fourier transform and take a slice in your frequency wave number spectrum, and you would get a slope of a line which would be away from these linear dispersion relation, and this would give the current speed or the speed of the advective surface or the features that are propagating forward. For more information, you could bug Professor Laksak about this. Now, moving on to another form of velocimetry technique, it is an active infrared imaging. This active infrared imaging for calculating velocity was first used by, one of the first people who used it was Veron et al., and this work was published in 2008. So it's hard to see over here, but then these red spots, oh, my hands are shaking. These red spots, right here, 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 and all these locations are what are remotely heated thermal spots on an already on the water surface, right? The background features are just shown in this background color, but then these are the spots which are marked, and that is at, say, time t1, and this image is at a different time, delta t. So you'd see, what's to see here is that these spots advected forward, and using this frame by frame advection of the spot, you could calculate your velocity measurement. You could get your velocity measurement, and also these measurements are Lagrangian in nature. So you follow the velocity field, you follow the particles. So you could get a particle track right there, something like that. Now, that was back in 2008. A more recent work done by Scalar et al. In 2020 used the same method, but a more structured grid, more regular grid, and more number of spots. The top figure is the raw thermal infrared image. The bottom plot shows the position of the spot in previous frame, and then the new location of the spot, and using that difference, you could calculate your velocity field at the surface. Now, let's talk about what we are doing. We did our experiments for the work that I'm about to present at University of Miami. The University of Miami houses the sustained tank. This tank has the capability of filling water up to half of its height, which is shown here, and the rest half is an open loop wind tunnel system where wind could flow. Right, and this is also equipped with a wave maker, a beach at the end to kill off all the energy. The air comes in from here and moves up. Now, a blown up view of this is shown here. This is blown up view. We have a mid-wave infrared camera, our active thermal marking system. Our active thermal marking system has two components. The first one is a mid-wave infrared camera and a carbon dioxide laser. Now, let's talk about what does the system does essentially. So water is opaque to long wave radiation. What the carbon dioxide laser does is that it emits radiation in long wave infrared region. Now, these long wave infrared region, water is opaque to this long wave infrared intensity coming in. So that means that all the energy are deposited as spots, like these on the surface, which is what printing of the thermal spots are. Now, once we have these thermal spots printed, that means small patches of water has been heated up, right? How do we measure? We image that using a mid-wave infrared camera, which has an optical depth of 32.227 micrometers, which is what our reference of true surface is, which is what our interpretation of true surface is, 32.227 micrometers from where the actual surface starts. So it's pretty close to the surface. It's actually the surface. Let's look at what these grayscale images, the raw grayscale images look like. So this is an example grayscale image of a run. So the fluctuation of the grayscale image is the temperature of the water is, and plus 2 degrees centigrade is what the bright regions are. It's very important that we do not cross, we have to maintain a temperature that is close to 1 or 2 degrees centigrade, because we want to avoid to set off any new circulation pattern within the thin layers. All right, Another thing, we have a spatial resolution of 1 millimeter. Our field of view is 1.28 meters to across 1.023 meters, and sampling rate is 50 hertz, and our temperature resolution is less than 20 millikelvin. So let's go back a couple of slides and then see what we are actually able to get from our wish list, right? So we have simultaneous spatial velocity measurements at air-water interface. We have unobtrusive measurement. We have high spatial and temporal resolution. What we do not have is a structured grid. These are Lagrangian measurement. We follow a spot, so they go where they go, and we do not end up with a structured grid. So if you remember, I mentioned a challenge that came up was how do you calculate the velocity gradient of an unstructured grid? I'll leave that question unanswered for now, but we will come back to that. So before we move further, let's look at what are the conditions that we studied as part of the Miami's sustained lab experiment. So we had all these wave conditions, summarized wave conditions, and for the purposes of keeping our discussion limited, we did not consider any 1.2 hertz wave. We only considered 0.58 hertz wave, and we had different number of ensemble repeats, which were successfully processed. All right, so we want to know what the non-linearity of these waves are, because they do deviate from our small amplitude and small slope assumption that we have for our linear wave theory. So looking at that, let's just consider 0.58 hertz wave. So 0.58 hertz wave are the circle spots. They edge right around a third order correction, which will be required for the Stokes wave solution. We do that by considering third order Stokes wave solution. So just to maintain uniformity and to incorporate all these conditions, we used a third order solution whenever we construct a theoretical solution from here onwards. So image preprocessing. If you remember the images that were displayed, the raw images, there were background features which were traveling, and also when we did these measurements, there was a very wide varying temperature range for the water. And a log scale plot of our grayscale, our raw grayscale image looks something like that. Now, we needed to do the filtering. So what we chose was a morphological operation where we did a top hat filter and a bottom hat filter. We operated a top hat filter and a bottom hat filter and then added them together. And we end up with an image that looks something like this. It's hard to tell the difference. Let's quantify what the difference was. A good way for quantifying it would be, a good way to quantify contrast stretching would be to just plot a binarized image, a binarized version of the grayscale image. Let's see how much better we do with it. Turns out we do a good bit better. We are able to find or get spots right where it has gone into a decay region, which were not before, right? So the filtering operation works. But the flip side of the coin is that these spots are around in the location where it has already gone through significant amount of decay. It's no longer the strongest, brightest spot there. Right, so that makes it susceptible to jumps, right? Jumps because there would be a warm feature passing by, and the algorithm would go, oh, there's a warm feature passing by, let's hinge on to that. So that we created ourselves another problem where we want to remove false detections. So to remove false detections, we resorted to velocimetric quality control. Now, this is the plot that I just showed, or this is this plot right here. This is the detected version of it. These are all the detected spots. You see there are unnecessary or false detection right there. There are false detections all over the places. So we want to get rid of it. To get rid of that, we used three different quality control conditions. The first one was where we restricted our spot lifetime to 5 milliseconds. We rejected any spot which was less than 5 milliseconds in lifetime. We capped the upper limit of a spot's lifetime to 1 second. To 1 second, yes. That reduced the susceptibility to jump, but did not remove it all the way. To do that, we then did a spot intensity lineage-based processing, where we looked at, say, if these are all the new spots being detected in an image, or in this image right here. What we do is we categorize them based on using a k-mean cluster, using three k-mean cluster. The first cluster would hold all the highest intensity spots. The second would hold slightly less intense spot, but then this does not start anywhere around here. This is just noise, which stays noise. So if we track the history from this frame onwards to different number of frames as a time series, as Lagrangian time series of spot intensity history, the actual spot shows a decay, an exponential decay like that, but noises, they just stay consistently over here, or moves, boom, jump, and then goes back. So these are jumps these are ejected spots which were duplicated because as a consequence of the jump. And the third filtering criteria was to use a Lagrangian velocity to see what the Lagrangian velocity field looks like. If we plot just the time history of it. So this is the Lagrangian U and V velocity for one spot, and this, because we have Lagrangian velocity, we can track it through different frames. So smooth, and then it jumps around, which shows that it just jumped around here for a different, better, higher intensity feature passing by, right? So we reject we cut it off. We cut off our contribution from this spot right here. Okay. So having implemented these three quality control criteria, we end up with something like this, which is much more cleaner and does the same job, right? Has a good number of spots that are detected. It rejects any spot which could have been the noise. So we have spot detections, right? Where do we go from there? We calculate our surface velocity. How do we calculate it? We have a spot, as Savlev et al. 2020 did. We have a spot in this frame, spot in the next frame. We divide the distance that it traveled by the time difference between it. Well, you get your velocity. Now, these velocity measurements that we had is for calibration which was done on still water. These water was not undulating, these water were not moving, they were just flat, plain water, right? So that is our camera calibration plane, but our wavy measurement plane, but our measurement plane is wavy. It has a certain height and then it also goes down, right? Now, sensitivity studies showed that because of these unaccounted magnification of the spots, what you end up with is plus or minus 4.616% error in the most extreme cases, the wave crest and the wave trough. Now, another source of error in these measurements are the slope of the wave, because a wave traveled down. If you're looking right from the top, what you see is the spot moving from here to here, but in reality, it is moving according to the slope of the wave. So we need to factor for that. It's not a very big error in this case, in 0.58 hertz case, which would all be here clustered together. But in more nonlinear cases, which we are not considering here, but in more nonlinear cases, this error is significant. Right. How do we correct for these errors? And along with correction for these errors, how do we get the elevation and the phase measurement for each spot? So for that, we sample velocity at the center of the frame, right? That's Eulerian measurement, right? Eulerian measurement of a surface wave passing through, right? A Eulerian measurement would give velocity measurements like this. The plot that you see, the data that you see here are the observations. Now, what we do with this is that we fed this data to theoretical solution given of the cylindrical wave equation given by Stokes' first, second, and third order solution. So how do they look? So this is your first order solution, right? A characteristic of first order solution is that they have equal magnitude at wave crest and wave trough. A difference is the second order solution. The second order solution is more peaked, but not as shallow in the trough. This is because of the nonlinearity of the waves. And then the third order solution plots right on top of the second order solution because as we showed earlier in the Lemate plot, our categorization, second order correction would have sufficed. The third order correction for these waves, for 0.58 Hertz wave, would just be 0. Only second order corrections would suffice, but nonetheless, because we wrote the code, we take third order. So doing all that gave us our elevation and phase of each spot, right? What you could do, before we look at that, I always wanted to do this, but there we go. This is what wave phase conditional averaging is. You have surface, you have your spots. These spots are at a particular location in X. They have a look, if this X, you can calculate the phase of the spot using kx minus omega t plus the offset. And each one of these spot bins will have some measurement that, and then within this bin, you calculate your wave conditional phase conditional averaging within each of these bins like that. If we have 3 measurements here, this 3 corresponds to the 3 points, theta 1, theta 2, theta 3. If you have more number of points, it's just taking average, but binning is what's important. So if you do that, we did that and we plotted our surface elevation as a function of phase, right? What we get out of this is how the surface elevation changes as a function of phase. So our wave crests are located at phase 0 and our wave troughs are located at pi and minus pi. Now, the first panel, or in this plot, shows a comparison between what we obtained from our first, second, and third order solutions to independent UDM measurement, which is the square black filled markers. They compare well. Now, once the comparison is done, we show our 2 centimeter, 4 centimeter, 6 centimeter wave elevation and the third order fit to it. They show good comparison between the elevation that we have. Now, if you remember, because now that we have our elevation, we have our slope because of the elevation. So the slope would be, if eta is our elevation, the slope would be d eta over dx. The errors, so let's see, we have our eta, and we can correct now for elevation correction using that formula. We can do a correction for slope using this formula, and voila, we have our corrected measurements. So this becomes we go from plane measurements to projected planar measurements. These are corrected for wave elevation and wave slopes. Doing the same, we can plot our surface velocity as a function of phase. The solid lines in here shows wave shape, scaled wave shape, scaled according to the wave velocity. Okay, we talked about how we could do averaging, average quantities, but we also have spatial data right there. We talked about how to we talked about that we need to calculate velocity gradient. We have spatial data. We can calculate our du dx, du dy, dv dx, dv dy, things like that. We can. How? So our first basically we first were like let's start with a central difference method using a nearest neighbor approach. We pick a circle at the center, we find all the nearest neighboring points, we divide it in different phases around the wave, around the circle in arcs, and the difference between this and then would give you a cross-time gradient. Spots included in the cross-time gradient, that might be off. But if you take the difference between the velocity and calculate it, it get you. This did not work out well. This canceled off some of our measurement values. So we moved on to a different method of estimating surface velocity gradient from an unstructured grid. So what do? We pick out the same nearest neighboring points, so all these points right here, but now we form a cluster of it like that. So say if we are measuring U velocity across tank, along tank, and we form a cluster of this, we find the normal projection, the normal to it, the normal to the surface, project it in X and Y, or the spanwise and streamwise distances, and we calculate our df, dx, and df, dy. F could be U and V here. Okay, moving on. So what does the instantaneous velocity gradient would look like? What do we do with it? What do we do with del U, del X, del U, del Y? We calculate different quantities, which would give us surface divergence, surface vorticity, surface shear, and surface strain. And this is it. So this is a single snapshot. The vectors, the arrows shows the direction and the magnitude of the velocity. The color map shows divergence, vorticity, shear, and strain, all normalized between -1 and 1. So this is one instant, one snapshot. Let's look at a video because that just is cool. So yeah, it just shows the. Now let us see, like, can we show that as a function of phase? So how do we categorize that? Oh, not that. Like that. So instead of averaging in the y direction, we don't average it in the y direction, we just collect it. And we have our phase and y, right? Which is what you see here in the plot on the right. So you're not averaging anything, you're just binning it and then plotting it in the 2D space right there, like that. So these are instantaneous measurements. Now, we want to talk about phase conditional long tank gradient, du dx. We have our velocity gradient. We want to compare it to how does that compares with. We want to see how does that compares with the theoretical values as obtained from the third order Stokes solution. So because Stokes solution would give you phi, which is velocity potential, you can calculate your u del phi over del x, and then you can calculate del u over del x, because all of that is just expressions, right? Here we show du dx non-normalized, because panel B, C, and D shows normalized du dx to see how that compares. But this plot of the panel A shows just du dx as obtained from the measurements, and compared that to the third order du dx obtained from the solutions of the theoretical values. Strain, the same, just a point, these compare well with the du dx. The observed du dx compares well with the theoretical du dx's. The strain, this is the strain on the surface. Right, and these strains, du dx, strain star is normalized by du dx, theoretical du dx's. Okay, what we have our divergence, strain, shear, vorticity. What can we do from there onwards? What we can do is look at the Craig-Leibovich equation. In that equation, we have this term vortex force. Here, US is the Stokes drift velocity. Stokes drift velocity looks something like that. This is taken from Wikipedia. For a deep wave, it looks something like that. And for a shallow wave, that. So Stokes wave Stokes drift velocity is preferentially oriented in the spanwise direction. Omega z is preferentially in the vertical direction. If you take a cross product of it, it would be oriented in the cross time direction. US cross omega. Now, what else that does? So let's say we calculated our vortex force from right here, and that looks, the spanwise distribution of it looks something like this, right? So this is our y, this is our span. We have a positive vortex force, a region of positive vortex force, and then regions of negative vortex force. This would push the water in these directions, away from where they are. So this would represent a divergence zone. Moving on, an orientation like this would represent convergence zone. That would represent the water being pushed inwards as compared to the divergence zones. So at this point, let's talk about what phasograms are. We'll very quickly go over what phasograms are. So we have these spot information, calculated velocity values, gradients, all these things stored at these nodes for a frame at a timestamp. Now to work with, let's take a cartoon of that, right? So this just represents the same image at time t, x and y. We can calculate the phase v1 kx1 minus omega t, and we can do that for all these spots or the measurement nodes. Once we do that, we can construct a three-dimensional space. In a three-dimensional space, we can start stacking it based off on what its phase information is, phase value is, and then at what time we are stacking it at. So that would look something like this. At where once the phase value reaches 0, it loops over to 4 pi, and the rest of the measurements are plotted on this side. So moving to this, right? So that creates our three-dimensional phasogram. What do we do with that? We take an average. We can look at the phase distribution, which would be a function of, which would incorporate time as well as a function of spanwise distance. So how do we use that? We use that by averaging a bunch of grayscale images together. So the same concept, kx minus omega t plus phi, but for grayscale images. So you stack them together, take an average, as was shown in the previous plot right there, this plot. You take an average, and in very few cases of all the runs that we had, we observed these long streak of dark regions and then bright regions, and then long streak of these dark regions were sandwiched between two bright regions, right? So that talks something about Langmuir circulations that goes on that line, but then we won't call it Langmuir circulation because these are really shallow water flows. But so we'll just call it a consequence of vortex forces. So we have these convergence zone, this black region, and then the divergence zone are the bright regions. So if we collapse the whole thing in the phase direction, so sorry, x-axis is phase here, this x-axis is phase. If we collapse the whole plot in the phase direction, right, and we will end up with this intensity, spanwise intensity distribution. So in these spanwise intensity distribution, these maxima and minima region shows where the convergence and divergence regions are, and the difference between this location and that location would give us our eddy diameter from images. So this is eddy diameter as calculated from an image. Now this is the vortex force contour map right here, which was calculated using US cross omega and then stacked up in the phasogram and then averaged, right? The vortex force is a second order term. It accumulates over time, and these consistent regions of these vortex forces cross over, which was shown in the previous slide. These consistent regions of vortex force crossover, the crossover of vortex force between minus to positive, the change of sign, the location. If we track these within each of these bends, small bends, what we would end up with is this plot, something like that, where each individual locations are just plotted with a thin transparent strip, and as they accumulate over each other, they darken out. Now, these consistent forcing regions, if we want to identify these consistent forcing regions, the location of the darkest region is where all these, the centroid of the location of these darkest regions are where the vortex force is consistently acting over and over again, implementing these sideways force. So we'll call this difference over here as eddy diameter as calculated from vortex force measurements. Now, if we repeat these experiments, if we repeat that measurement of eddy diameter over 4 different runs, which were about 650 or 700 measurements over 350 wave period, and do a 1:1 comparison. So the eddy diameter compares fairly well with the eddy diameter as obtained from vortex force measurements, and the image is compared decently well. Okay, that was about the dynamics on the surface. Let's really quickly talk about the turbulence statistics, and then what happens to these statistics as a result of interaction of current with wave field, right? In the presence of wind speed and all that. So we do a triple decomposition of our velocity field, and then if we denote our directional TKE component by qx square and qy square. So this is our plot, this is our result for this panel A, C, and D are qx square, the streamwise turbulent kinetic energy at the surface, and panel B, D, and F are spanwise turbulent kinetic energy. Something to observe here is that the dashed line that you see right here is a wind-only case. So along with all these wavy field measurement, we also had no wave measurement where there was only wind speed, a constant wind speed that was blowing over. So we wanted to compare what happens in the presence and in the absence of a surface wave. Now, this plot just shows that at low wind speeds, it doesn't, the turbulent kinetic energy is higher than the wind-only case. But as we start to increase the wind speed, something unique happens, which is that it starts to sheltering mechanism. So it starts to shelter regions of the wave from direct wind inputs. That happens much more significantly as you move to a really high wind speed. So most of the turbulent kinetic energy in the wave field is actually not high, but like counterintuitively lesser as the wind speed goes up. We do not see, because these were unidirectional wave, we do not see any significant change in the TKE values of the spanwise direction, except that at the highest wind speed, the wind-only case and the wave cases match each other. We wanted to calculate the turbulent fluxes through the surface of an ocean wave. We used the structure function. I'm grateful for Dr. Catherine Adler, for this next plot because he suggested something like this. Using the structure function, we fit our data to an r to the power 2/3 fit. Using that, we have our R, we have our structure function, which we observe. This is the 3-dimensional turbulence structure function form, and we obtain our epsilon, our TK dissipation rate from there, from this fit, and a phase, and this is our phase conditional average TK dissipation rate, which follows closely what happens to the TK, a similar sheltering mechanism. So the TK result was something that was observed by Savlev et al. 2020. He did not do TK dissipation rate, but this is fairly agrees with the results of the study that were done very close to the surface, not at the surface, but slightly below the surface. So you see a similar bump at the wave crest, but then it gets sheltered. as the wind speed increases. Now, this plot is a combination of all the runs averaged over all the phases. So the plots shown before was phase condition, was a function of phase. Now it's just ensemble averaging bulk turbulent kinetic energy and the dissipation rate. So this panel A and B are the turbulent kinetic energy in X direction and Y direction. You see the effect of sheltering because at low wind speed, this spot is below all the wave amplitude or below all the wave cases. But then at the highest wind speed, the TKE for the wind only case is higher than any of the cases which has wave in it. The TKE dissipation rate, the TKE for in the spanwise direction, it just asymptotes to a single value. TKE dissipation rate shows something similar in the spanwise direction as it does for the TKE. And this is our plot for the TKE dissipation rate in Y direction. Now, I want to point out what's about to come. We are working on a data set we are working on this data set now, where we have a line marker, which would give us very fine resolution spatial velocity. And that's about it. And this is a video which just shows the contour vortex force contour map, but as a video. So, thank you.
Right. Anybody has any question?
Nice job on the structure function calculations. I was wondering, is it complicated getting the structure function in Y when you have the linear circulations? Like, does that introduce like a lot of energy at the unit scale of the quantum cells?
So these cells, these vertical counter-rotating cells could be counted with language circulation, but they were restricted to very few cases which had really high temperature, high wind, high amplitude. So for a conclusive analysis of the question that you asked would be to study specifically what's happening in the language, and that's something not we did.
Yeah, thank you, appreciate all of that, trying to soak it all in. So the cases where you ran wind but didn't generate waves, presumably the wind is still interacting with the surface and generating small waves.
Yes.
You have capillary waves, how much does that, like the generation region in the ocean, there's not very many places where the wind is blowing and there's no waves.
Yeah.
Right? It's mostly always wave with wind. How do you translate that to ocean fluxes? Because you're showing that there's more turbulence under the wind case without waves because of the sheltering effects.
This for wind only case or?
Yeah, for the wind only case, I'm just trying to reconcile what that means.
Yeah. So for the wind only cases, there would be some capillary scale waves that would be generated, but the resolution that we have for our grid does not allow us to capture that or isolate that, separate it out from our turbulent measurement for now. So I don't know exactly if there's a study which looks into what the capillary wave does to the turbulence spectra. Just the capillary waves, because they are almost of similar size, similar length scales. But the gravity scale wave does not affect the turbulence spectra, where in the inertial subrange, it mostly is concentrated towards lower wave numbers or larger scales. But that would be an analysis we would do in this work right here, where we have, so this was the original grid spacing in the 2022 measurement, this is 2024. And because we learned, we had our lessons that we won't be able to separate out or even calculate a spectra using these grid measurements, which is why we introduced these line measurements, which is gonna pop up any second. This right here. So we can calculate our turbulent spectra. We could show in the cases where there are capillary scale waves being generated on the surface, we could look at what happens to the spectra because of those waves or capillary scale rotation.
Thank you, yeah, thanks.
Yeah, we do have one online question. Jade says, great talk. From my understanding, you calculated the shape / elevation of the wave based on knowledge that you were driving it with a known frequency with the wave maker. How would you figure that out in the field?
I don't know the answer to that. Jade, sorry, I don't know the answer to that, but I'll get back to you. Is there anyone? Yes.
I might have missed this. When you showed your like raw data at the very beginning,
Yeah.
and then you said the resolution was like 1 millimeter and the field of view was a meter.
Yeah.
I was trying to match that to like when I saw the video, it looked like the spots were bigger.
Yeah, sorry. So the spots are about 2 to 3 centimeters in size, but the spatial resolution of the camera is 1 millimeter per pixel.
Okay.
So this, and that's why I was talking about the grid resolution.
Yeah.
The grid resolution is 5 mm, which will allow us to capture anything of 10 mm in size, or 5.5, so 11 mm in size. So our grid resolution is not that big, but the line marker in the 2024 study we have the resolution of our measurements at 1 millimeter per pixel.
Oh, cool.
So we have a higher resolution, which is an upcoming work.
Does anyone have any further questions? Okay, you go.
Yeah, I have another one. So you talked about getting your eddy diameters from these figures actually that are up on the screen now. Can you estimate, what would you have before the spike? Can you estimate the eddy diameter as a function of frequency? By looking at those panels on the right, can you calculate a spectrum of that? Or maybe an ensemble spectrum for the number of realizations? Can you get eddy diameter as a function of frequency?
Use this plot to calculate.
It should be the function of rate, so eddy diameter is a function of rate. So as opposed to energetic eddy diameters are, yeah.
That could be something we look into next now. And it helps to have a better resolution
Yeah.
in the next study. This has a good resolution, but
And is spectra difficult if you don't have regular spacing?
yeah, we cannot calculate spectra if we do not have regular spacing of the grids. Which is one of the biggest reasons why we have to move to the line markers. So because of the uneven spacing, so it's 2 centimeter in one frame and then like separated by a lot in the next one.
Anyone else with a question? Okay, then I'll go. So for the structure function, okay, what is your vector spacing?
The vector spacing would be 5 centimeter.
Okay. So how do you reckon, I mean, you're obviously missing scales in between those 5 centimeters.
Yeah.
It's not like, their smallest scale is probably at the 5 centimeters. It's gonna be on a fraction of a millimeter. How do you reckon that would affect the shape of the structure?
Well, the R to the power 2/3 law would stay as is. It's just that you'll fill the spots in between. Right?
But that would affect the constant, right? Which you're using.
No,
to
the
build
constant.
it.
So the TK dissipation rate would be given by a constant. Yeah. So it's this quantity times R to the power 2/3, and the C nu is a constant, right? And R to the power 2/3 is just a fit, which even if you fill it up with infinite number of points, the slope is not going to change because C times epsilon to the power 2/3, it is going to stay constant.
But that's under the assumption that things are isotropic.
Well, that's a whole another question of 3-dimensional and 2-dimensional turbulence. If we are assuming 3-dimensional, yes.
All right. Anyone else has a question? Then I guess.